Hi, our next talk is going to be by Yinchen Liu, about quantum advantage from measurement-induced entanglement in random shallow circuits.
Hello, let's get started. I'm going to tell you about quantum advantage from measurement-induced entanglement in random shallow circuits. This is joint work with Adam Bene, David Gosset, and Mehdi Soleimanifar. Okay, so this talk is about the complexity of classically simulating shallow random quantum circuits. And shallow will mean constant depth throughout this talk. Our overall motivation is to better understand whether shallow random quantum circuits give rise to some form of quantum advantage. Okay, so in our work, we identify a novel connection between two previously separate lines of work involving quantum advantage in shallow quantum circuits. The first line of work demonstrates unconditionally a form of quantum depth advantage using 2D shallow Clifford circuits. In the second line of work, the authors give compelling numerical and analytical evidence for an intriguing phase transition in the time complexity of simulating 2D shallow random quantum circuits with composed of Haar random gates. And the connection is established via a concept known as measurement-induced entanglement. And let's see how this works. So in the first part of the talk, I wish to highlight how measurement-induced entanglement played a fundamental role in the kind of quantum depth advantage established in the first line of work. So I would like to begin with a quick summary of the main results by Bravi, Gosset, and Kant. In this paper, the authors considered a classical input, classical output search problem called the 2D hidden linear function problem. They showed that a quantum computer can solve all instances of this problem with certainty by running a controlled 2D shallow Clifford circuit. They also showed that unconditionally, any probabilistic classical circuit with bounded fan-in that can solve all instances of this problem must have at least log n depth. Therefore, it's a constant versus log n depth separation. So what do their results imply in terms of the hardness of classically simulating shallow Clifford circuits? Well, informally, the results imply that 2D shallow Clifford circuits cannot be classically simulated by shallow probabilistic classical circuits with bounded fan-in. And let me explain what these terms mean. So firstly, in a 2D quantum circuit, we have n qubits living on the vertices of a root n by root n grid. And 2-qubit gates can only be applied to neighboring qubits either horizontally, right, like this, or vertically, like this in layers. And circuit depth is the number of layers of gates. So shallow circuits have constantly many layers. So the animation illustrates one example of a circuit architecture or template that specifies where to apply each gate, but not the actual unitary transformation being applied. So in a Haar random quantum circuit, each gate is sampled independently from the Haar measure. In a Clifford circuit, each gate is a Clifford unitary. In a random Clifford circuit, each gate is independently a uniformly random 2-qubit Clifford operator. Okay, so a probabilistic classical circuit in our context takes as input another Clifford circuit specified by a list of gates and outputs an n-bit string Z sampled from some distribution P sub u, with u being the input Clifford circuit. So in this example, the input consists of 6 gates and the output has 4 bits. The goal or objective for the classical circuit is to sample from a distribution P sub u as close as possible to the output distribution of the Clifford circuit u, with u being applied to the all-zero state and measured in the computational basis. Right? So the job of the classical circuit is to simulate the Clifford circuit. And here, the quantum circuit architecture is fixed and hard-coded into the classical circuit, so it knows how to interpret its inputs. Without going into too much detail, the fan-in k and depth d conditions imply that each output bit of the classical circuit will only depend on, at most, k to the d of the input gates. So in particular, if the classical circuit has constant fan-in and constant depth, that each output bit can only depend on constantly many input gates. So this is the informal theorem statement again. So the authors proved this theorem by fixing an architecture and then picking the gates adversarially for each possible classical simulator that's a shallow probabilistic classical circuit with bounded fan-in. And let's see where measurement-induced entanglement, or MIE, appears in their construction. So here's the grid of qubits again. Right? So the plan is for every possible simulator, we construct a shallow Clifford circuit adversarially to make the simulator fail. Okay, so step 1, choose 3 qubits Hi and J with disjoint Lie cones with respect to the classical circuit, and that the pairwise L1 distances between the qubits Hi and J are all even on the grid. Here, the classical Lie cone of a qubit is the forward Lie cone of the last gate acting on that qubit when serving as an input to the classical simulator. Okay, step 2, prepare a cycle graph state right through the qubits Hij by applying a layer of Hadamard and 2 layers of control Z gates. Now, because the qubits Hij, they could be very far apart on the grid, and when that happens, they also have disjoint backward Lie cones in the quantum circuit that prepares the cycle graph state. Okay, next, they measure every qubit except Hij in the X basis, which can be implemented by applying a Hadamard and measuring in the computational basis. Okay, now something very interesting happens. Because the pairwise distances between Hi and J are all even, the pure 3-qubit post-measurement state phi of Hij will be the GHZ state up to a local change of basis. In other words, the state phi is locally Clifford equivalent to the GHZ state. Right? Now this is an instance of measurement-induced entanglement. Why measurement-induced? Well, when the qubits Hij have disjoint Lie cones in the Clifford circuit that prepares the graph state, before measuring all other qubits in the X spaces, the reduced state of Hij is a product state. So there's no entanglement among Hij before measuring all other qubits. However, after the measurement, and it's important not to throw away the measurement outcomes, to get a pure post-measurement state. The pure post-measurement state of Hij is locally Clifford equivalent to the GHZ state. It becomes entangled. Okay, so back to the construction. For the third step, they choose to measure the qubits Hij in either the X basis or the Y basis. So this choice depends on the classical simulator circuit, but it's a deterministic choice. So thus far, we've completely specified an adversarial shallow Clifford circuit. But why can't the classical circuit simulate this particular Clifford circuit? It's because the measurement outcomes of GHZ-type states always satisfy some global constraint. Right? For example, maybe the parity of the outcomes must be 0. But because the qubits Hij, they have disjoint Lie cones with respect to the classical circuit, the classical simulator circuit, it cannot perfectly capture this long-range global correlation. Right? Perhaps the classical circuit, it cannot force itself to never output something like 1, 1, 1. So in any case, the situation here is similar to analyzing the GHZ non-local game. Okay, so we've just explained a clever construction and saw how tripartite MIE is a key ingredient, right? It played a key role in embarrassing the classical simulator circuit. And now the question becomes, how necessary was it for the adversary to even look at the classical simulator circuit at all? Right? How about replacing the tailored construction with a random shallow Clifford circuit? So here are the 3 main steps of the argument again. So for the first step, right, instead of choosing the qubits Hij carefully, well, it's not hard to see that if you just blindly choose 3 qubits uniformly at random, then with high probability, they will have disjoint Lie cones with respect to a classical circuit having sufficiently small fan-in and constant depth. And for the third step, right, instead of choosing the measurement bases for the qubits Hij carefully, or if you just pick X, Y, or Z bases randomly for these 3 qubits, it feels like it should be OK because you would make a correct guess with probability at least 1/27, right? So you will lose at most a constant factor. But how about the second step? Well, if you think about it, the fact that the GHZ-type state it arose from measuring all but 3 qubits in a cycle graph state, that didn't seem to be so critical. But it feels like step 3 would kick in so long as we can force 3 distant qubits to be in a GHZ-type state somehow, and it may be possible to adapt the proof, right, if shallow random Clifford circuits give rise to tripartite MIE. So before we continue, it's instructive to define the tripartite MIE property for random Clifford circuits a bit more carefully. So we say 3 qubits Hij exhibit tripartite MIE in the stabilizer state psi if the 3 qubits are in a tripartite entangled state after measuring all other qubits of psi in the computational basis. It's a computational basis. Okay. It's a well-known fact that if a 3-qubit stabilizer state is tripartite entangled, then it's necessarily locally Clifford equivalent to the GHZ state. Okay, then we say a distribution of random Clifford circuits has the long-range tripartite MIE property if with at least some constant probability over the choice of a random circuit in Hij, the 3 qubits exhibit tripartite MIE in the output state of the circuit. So here the 3 qubits are chosen uniformly at random, and long range refers to the requirement that the probability is at least some constant, even if Hij could be very far apart as n grows. So in this definition, the random circuits are not assumed to be shallow. So it becomes a question of whether shallow random Clifford circuits satisfy the long-range tripartite MIE property. Okay, so our main result in the first part can be summarized informally as this: a tripartite MIE is all you need theorem. It says that if a distribution of random shallow Clifford circuits satisfies the long-range tripartite MIE property, then they cannot be classically simulated by shallow probabilistic classical circuits with bounded fan-in. Of course, we use other depth-insensitive properties of random Clifford circuits, right? But surprisingly, long-range tripartite MIE stands out as the only depth-sensitive assumption about shallow random Clifford circuits needed to get a quantum depth advantage. So now, the boiling question is do shallow random Clifford circuits exhibit long-range tripartite MIE? Because otherwise, what's the point if the assumption is never satisfied? Okay, so that leads to the next part of the talk, where I'll explain how our work connects to phase transitions observed numerically and analytically in 2D shallow random quantum circuits with composed of Haar random gates, right? Not Clifford gates. Okay. In our work, we consider a very concrete notion of bipartite MIE for 2D random quantum circuits. We partition the grid into 3 disjoint regions A, B, and C, where A contains a single qubit, B is an L by L square block of qubits surrounding A, and C contains the rest of the qubits. Right, suppose this L site length is big enough so that there's no entanglement between A and C inside the output state of a 2D shallow quantum circuit U. Then we measure all qubits in B in the computational basis, right, to get a pure post-measurement state phi on AC. Now, entanglement between A and C gets created if and only if the reduced state of the qubit A is not pure after the measurement. Okay, in the context of our definitions of in the context of our ABC tripartition and measuring everything in B, we say a distribution of 2D random quantum circuits has short-range MIE if the expected purity of the qubit A approaches 1 exponentially in the site length of B with randomness over both the random circuit distribution and the measurement outcomes on B. In contrast, we say a distribution of 2D random quantum circuits has long-range MIE if the expected purity of the qubit A is always bounded away from 1 by some constant, no matter how big B is, so long as C contains at least 1 qubit. It's worth mentioning that our definitions of short and long-range MIE do not cover all possibilities, because it could be that for some reasonable architecture of 2D random quantum circuits, the expected purity of A, it does approach 1 as L increases, but not exponentially. Okay. So now we can state a version of the conjectures by Knapp et al. In terms of our definitions of short and long-range MIE. So it's conjectured that there exists a constant critical depth D star such that 2D random quantum circuits composed of Haar random gates with depth less than D star have short-range MIE, and with depth at least D star have long-range MIE. So there's a sharp MIE phase transition at depth D star. Moreover, 2D random quantum circuits with short-range MIE can be efficiently classically simulated, but those with long-range MIE cannot be efficiently classically simulated. So I'd say it's already very surprising to me that there could be any sort of non-trivial phase transition in shallow random quantum circuits. In a way, this is conjecturing not only 1, but 2 coinciding phase transitions. And strikingly, points 3 and 4, the conjecture that measurement-induced entanglement is the necessary and sufficient condition for quantum time advantage in 2D random quantum circuits composed of Haar random gates. Okay, but do we know how to prove any of these? 1, 2, 3, any of these? Well, in our work, we give an efficient classical simulation algorithm for 2D random quantum circuits that satisfy a slightly stronger notion of short-range MIE that requires not just the whole circuit, but also sub-circuits to exhibit short-range MIE. Our algorithm is based on the gate-by-gate method, and it complements the patching algorithm given in the paper by Knapp et al. And then the breakthrough work of the previous talk actually proves long-range MIE with respect to a slightly different ABC tripartition, and for the brickwork architecture with qubit dimension at least 134 and depth exactly 4, but somehow unable to prove for higher depths like 5, 6, and so on. Even so, I'd say what's mainly lacking for this conjecture is that number 4, right, the hardness of classically simulating 2D random quantum circuits with long-range MIE, right, that remains wide open. Wide open, OK. So now relating back to the first part of the talk, can we state a similar depth version of this phase transition conjecture for random Clifford circuits? Well, surely it's always possible to state a similar conjecture by mimicking the previous one, just replacing some keywords. So this slide shows our attempt at that. So we officially conjecture that there exists a constant critical depth d star such that 2D random Clifford circuits with depth less than d star have short-range MIE, and with depth at least d star have long-range and long-range tripartite MIE. So there's an MIE phase transition at depth d star. Moreover, shallow random Clifford circuits with short-range MIE can be simulated by shallow probabilistic classical circuits with bounded fan-in, but those with long-range tripartite MIE cannot be simulated by such classical circuits. Okay, so in parallel to the Hall-random case, this conjectures that there exist coinciding phase transitions for quantum depth advantage and measurement-induced entanglement in random shallow Clifford circuits. Right? And that MIE is the key ingredient separating between simulability by shallow classical circuits and quantum depth advantage. Okay, so now if you stare at number 4, isn't this exactly our tripartite MIE is all you need theorem from before? And yes, indeed. So unlike in the Hall-random case, we do have a proof for number 4 in the Clifford case. Our classical simulation algorithm also works for Clifford circuits with the same caveat concerning a sub-circuit short-range MIE, and it can be parallelized to constant depth if the circuit to be simulated also has constant depth to begin with. The work of the previous talk also proves long-range tripartite MIE, although for a somewhat unusual family of 2D shallow random Clifford circuits. But nonetheless, combining with our tripartite MIE is all you need theorem, this leads to an end-to-end unconditional quantum depth advantage with some family of 2D shallow random Clifford circuits. So lastly, I would like to showcase what we can prove about the existence of long-range MIE in some family of 2D shallow random Clifford circuits. So here's the grid of qubits one last time. So we consider a coarse-grained architecture consisting of exactly 2 layers of coarse-grained gates. So the first layer of gates looks like this. Here, each gate is independently a random Clifford operator acting on tau squared qubits. Okay, and this is the second and final layer of gates. Here, each gate is also a tau squared qubit random Clifford gate. So this completely specifies this coarse-grained architecture. It's exactly 2 layers of big gates. So we prove that random coarse-grained Clifford circuits with tau squared being at least log n satisfy the long-range and long-range tripartite MIE properties. So as a result, we obtain an end-to-end unconditional quantum depth advantage against probabilistic classical circuits with fan-in poly log n and depth log n over log n using random coarse-grained Clifford circuits. So to summarize this talk in one sentence, right, our work identified a novel connection between 2 previously separate lines of work concerning quantum depth advantage in shallow Clifford circuits and quantum time advantage in shallow Hall-random quantum circuits via measurement-induced entanglement. Yeah, that's all I have to say. Thank you for your attention.
You have a question?
Okay, thank you. for the interesting talk. I have a question on relating the entanglement measure that you define for these via these three regions, A, B, C, where one is like a separating region. Are there any connections that you know of to information theoretic quantities of the ensemble of measurements you get on these qubits, like conditional mutual information between A and C, for example, or something similar?
Yeah. I feel like you get CMI if and only if there's MIE at a high level.
Like long range MIE, you say?
Long range MIE. Long range MIE if and only if the CMI between A and C is not 0, condition on B.
Thanks a lot.
Yeah.
Hey. Yeah, thanks for the nice talk. Oh, I'm right over here.
It's right there.
To your left. Yeah. So I was curious. In a follow-up work by Bravi, they showed the same unconditional quantum advantage for like noisy shallow circuits in 3D. But the way that they did this is by considering like an alternative non-local game that one could play that's based on like the Merman square game that works based on like having stacked copies of two one-dimensional cluster states. So I was wondering, do you feel like the same unconditional quantum advantage should hold for random shallow circuits in 1D as well? Or is there something like there's no long-range MIE for these kinds of models?
Yeah, for 1D constant depth, there's no long-range MIE. Right, but for 3D noisy, I don't know.
Okay, cool. Yeah, thanks a lot.
Any other questions? We still have time.
Still have time to take a picture. Yeah.
Okay, let's thank Calvin if
Yeah.
there's no more questions.